Hi, this is week 16 of AP Physics, and in this week we'll talk about pendulums and springs. For our lesson objectives, students will understand how the length of a pendulum affects its period. Students will also understand how the mass of a bob affects the period of an object attached to a spring. So we're going to go ahead and discuss first those pendulums and springs. Let's have a quick discussion of what is a pendulum. A pendulum could be an object attached to either a string or a rod. Here, the object at the bottom is referred to as a bob. Going straight down, that's referred to as the equilibrium point or the vertical, and its movement back and forth is referred to as simple harmonic motion. So that oscillation back and forth is simple harmonic motion, but the time it takes to complete one oscillation, the movement back and forth, is referred to as the period of a pendulum. So it says a simple pendulum of length L moves in with simple harmonic motion for small angular displacement from the vertical. How do you calculate the period? This is a formula for the period. And in it, uppercase T is the period measured in seconds, multiplied times m times pi, multiplied times the square root of L over G, which L is the length of the pendulum and G is gravity. The length is measured in meters and gravity 9.8 meters per second squared. For our calculations, we'll still go with 10 meters per second squared. Now, that's a pendulum. Now let's go ahead and talk a little bit about the forces that act on the pendulum. Alright, so there's a series of forces. Number one, gravity, of course, mg for gravity here. And there's also tension from the string. So how do we calculate the magnitude of the tension plus the force that restores the pendulum back to the equilibrium point? So we're going to go ahead and get this, the force of gravity, and break it down into its components. So I'm going to go ahead and draw an arrow here and there for our components. And this one right here, we're going to go ahead and figure for it. The angle, notice that an angle theta is adjacent, so therefore we should use cosine. So for the magnitude of this arrow right here, it's going to really be mg times cosine theta. And that's going to give us our force of gravity on the y-axis, this one. By the way, that'll be the same in magnitude as our force tension here. So I'm going to put an arrow going up. So that'll be the same length because they should be the same magnitude. Now what about the force that restores the pendulum back to the equilibrium point? How do we solve for that? Notice that this arrow is opposite our angle theta. So we're going to use mass times gravity times sine of theta. And that will give us our force of gravity on the x-axis, which is our force that restores us back to the equilibrium point. Next, I wanted to go ahead and compare what happens to those forces as we increase the angle. So for our second picture right here, you'll notice we have a much bigger angle than we do in the first. So let's go ahead and break down again the forces and notice the length of the arrows. So I'm going to go ahead and again I have to draw a right triangle. So look like that and that as well. The formulas will be the same, mg times cosine theta and mg times sine theta. But what I really want you to notice is the magnitude of the arrows. Since we have a larger angle, the force that's restoring the pendulum back to the equilibrium point is much larger when compared. Look at the magnitude of these two arrows, their length. Alright, they're not quite the same. This one is much larger when you have a larger arrow. On the other hand, look at the force tension. The force tension is smaller. The higher the angle goes, the smaller force tension. So that's the restorative force on the pendulum. Up next, we're going to go ahead and use this equation to go to solve for the period of a pendulum with 4 different lengths. So our first problem asks us the following. What is the relationship between period and the length of a string in a pendulum? So they also tell us that acceleration due to gravity is 10 meters per second squared. So is there a relationship between the length and the period? So we're going to go ahead and study that. We're going to go ahead and use this equation to figure out how does the length affect the period. So for our first trial, it's going to be length is 1 meter, then 2, 3, and then 4 meters. So we're going to go ahead and take a look at that. Then we're going to go ahead and graph it and attempt to linearize it so we can get the relationship. So let's go ahead and plug in the values for our first trial. So I'm going to put T1, it's going to be 2 pi multiplied times the length, which is 1, over acceleration due to gravity, which is 10. So we're going to put 1 divided by 10, square root that answer, and multiply it times 2 times 3.14 for pi. That's going to give me 1.99 seconds. Alright, then the next one, same formula, 2 pi, but it's going to be a 2. The length, now we are changing the length to 2. So we're making it longer. So what's going to happen to our period? Will our period be faster? Will our period be slower? So let's go ahead and work that one out. 2 over 10, square root the answer, multiply times 3.14 times 2. That'll give me 2.8 seconds. So we made the length longer. Now it took the pendulum longer to swing back and forth. Let's keep going. For our third trial, we have 3 meters. So it's going to be 3 over 10 square root multiply times 3.14 times 2. That's going to give us 3.44 seconds. And the last one is going to be trial 4, where our length is 4 meters. So it's going to go ahead and give us the following values. So it's going to be 4 divided by 10, square root the answer, multiply times 3.14 times 2. That gives us 3.98 seconds. Alright, so those are our values. 1.99, 2.80 seconds, 3.44 seconds, and 3.98 seconds. So we use our formula for the period of a pendulum to go ahead and figure out how long it will take it to swing back and forth at these lengths. Now, something I also want to point out is the relationship between these two values. Notice that 1.99, if you go ahead and you double, you go ahead and you get 3.98. Why is that significant? If you want to go ahead and double the length of a period to make it twice, the pendulum should take twice as long to swing back and forth, what would you have to do to the length? You would have to quadruple the length. So you need to make you want to double the period, you're going to have to quadruple the length of the pendulum to make that happen. Up next, we're going to go ahead and graph this data to see our relationship. So as we look at the data, we can see that as the length gets longer, we see the period also gets longer, so they're directly proportional. Alright, let's go ahead and take a look at that relationship as a graph. So here we have on the x-axis, we went ahead and put the length. On the period, we put that on the y-axis. And let's go ahead and graph these values. So a length of 1 meter is going to be 1.99. So 1 meter will be 1.99. That'll be somewhere over here. The 2 meters is going to be 2.8. So it'll be somewhere over here. At 3 meters, it'll be 3.44. So it'll be somewhere approximately here. And finally, at 4 meters, it'll be 3.98. 4 meters somewhere around here. And you can see a straight line, so we do a best fit line. And you see that linear relationship, yeah, they are directly proportional. Alright, so that takes care of this problem. In our next problem, we're going to go ahead and take a look at the movement of a mass attached to a spring, and also go ahead and calculate its period going back and forth. So in this picture right here, the dotted line represents the equilibrium point, and this more is a time-lapse picture of the spring and the mass moving back and forth, back and forth. And what they're trying to show is how it resembles the movement of a pendulum. So it says the period of an oscillating spring shares many similarities with the period of a pendulum, where the formulas almost look the same, where here's the period is equal to 2 pi multiplied times the square root of mass over the k, which is a constant of a spring. On their next slide, they ask us the following. It says, what is the relationship between the period and the mass of an object attached to a spring? And they tell us, assume that the spring constant is 10 newtons over meters, which is very similar to the previous problem we did where gravity was 10 meters per second squared. So let's go ahead and get these values. So here's the formula. Again, all that we're going to do is go ahead and multiply the m right here, and they tell us that the spring constant is 10. So it's going to go ahead and look the same as we had done previously, where it's going to be 1 kilogram over 10 newtons per meters. Here, that's for our first trial. Second trial will look the same, and but it's now 2 kilograms over 10 newtons per meter. Third trial, it's going to look like this: 3 kilograms over 10 newtons per meter. And finally, fourth trial will look like so. Alright, so now let's go ahead and do the calculations, and this time I'll write my answers here. So for the first one is 1 over 10.1, square root of our answer, multiplied times 2 times 3.14, which is pi, and we get our answer 1.99 in seconds. For our second problem, we get 2 divided by 10, square root of the answer, and then multiply 2 times 3.14. That's going to go ahead and give us the following. 2.81. Alright, next one, 3 over 10 times 2 times pi. This is going to give us 3.44. And the last one as well, we're going to go ahead and do that division. Square root it, multiply it times 2 times pi. It's going to give us 3.98. Here we go. Notice how it's the same values as the previous problem, so you see how the mass affects the period the same way the length affects the period. This one for a mass attached to a spring versus the other one was the period of a pendulum. Again, one more time, if you wanted to double the period, notice 1.99 here, 3.98, what you would have to do is quadruple the mass of the object attached to the spring. Alright, that takes care of this problem. Up next for us is example 10. In this problem they ask us the following. Using a small pendulum of length 0.171 meters, a geophysicist counts 72 complete swings in a time of 60 seconds. What is the value of G in this location? First of all, G, wouldn't you say, well, it's at 9.8? He's on planet Earth. Now, yeah, 9.8 is an average value, though. The value of G changes around the globe. So you could get something close to 9.8, but maybe not exactly that value. The next question that I wanted to address is, why did he allow the pendulum to swing 72 times over a minute? Why not just have it swing once to get the period, which we're going to need to solve this problem? The answer for that is, the more you allow it to swing, that can reduce error, as far as allowing it for you to start and stop your stopwatch within that fraction of a second it takes it to swing back and forth. That would be difficult. So it's a lot easier to get an accurate measurement for the period by having it oscillate more times and just keep time of how many oscillations it does over a period of time. So what exactly is the period of this pendulum? So for the period of the pendulum, it's going to go ahead and be the following. It's going to be 60 seconds, which is the amount it took to swing those 72 oscillations, divided by 72. So that's going to go ahead and give us the following. So 60 divided by 72, it is 0.833 seconds. That is the value for one oscillation to go back and forth. So that's very tough to get with just one swing. Can you accurately get less than a fraction of a second? And that's why the geophysicist allowed it to swing so many times before he actually collected the period. So now that we have our period, let's go ahead and get to figuring out for G. Alright, so for G, it's going to be the following. Length, by the way, 1.71 meters. Here's going to be our formula. Period is equal to 2 pi multiplied times the square root of L over G. So we're looking for G here. So I'm going to go ahead and move stuff around. I want to isolate the G. So I'm going to do that. First thing I'm going to do is I'm going to square both sides. So I can go ahead and get rid of the square root. So I'm going to square the T. So it's going to be T squared. Square the 2. So it's going to go ahead and give me 4. Square the pi. So that's just pi squared. Multiply times L over G. Alright, now I'm going to go ahead and move the G over here. So multiply both sides by G. That's gone. And next I want to isolate the G, get rid of the T squared. So I'm going to divide both sides by T squared. And giving us G is equal to 4 pi squared times L, the length, over the period squared. Alright, so that's our formula for G. Now if you have it, let's go ahead and plug in the numbers here. G is equal to 4 pi squared multiplied times the length, which is 0.171 meters, over the period, which was 0.833 seconds squared. Alright, so we plug it into the calculator. We're going to go ahead and get the following. 0.717 times pi squared times 4 divided by 0.833 squared. It's going to go ahead and give us a value of 9.719 meters per second squared. So just about 9.8, but not quite. Alright, that takes care of example 8. Let's go ahead and move along to the next problem. In this problem, in problem number 32, they ask you, is true or false? A simple pendulum of length 0.5 has a larger frequency of vibration than a simple pendulum of length 1 meter. Alright, does the smaller pendulum have a higher frequency? The answer for that, yeah, this will be a true answer. And we should take a look at the formula for the relationship between frequency and the period. Alright, frequency is the inverse of the period. So the smaller the period, the larger the frequency, since they're inverses of each other. So the smaller length will have a shorter period. So smaller value here will give you a larger frequency. On the other hand, the longer the length is, that means that it'll have the larger the period. And since they're inverses, a large period means a smaller frequency. So the answer for this one is true. A simple pendulum of length 0.5 would have a larger frequency than one of a length 1 meter. Let's go ahead and move on to our next problem. Number 33 says, what will be the period of a 0.17 meter pendulum on the moon where the acceleration due to gravity is 1.62 meters per second squared? So gravity on the moon is 1/6 of that on Earth. So they give us the value for G on the moon. So they want to know the period. So let's go ahead and figure it out. 2 pi L over G, and you square root that. So that's our formula. Let's go ahead and figure out what we get for the period. The length, 0.171 meters, over the gravity on the moon, 1.62 meters per second squared. Square root that, and that's going to give us our answer. Plug it into the calculator. 0.171 divided by 1.62. Square root that answer. Multiply it times pi. Multiply it times 2. And we get our period, which is 2.04 seconds. That will be our answer for problem number 33. Up next for us is problem number 34. In this problem, they ask you as the following. A pendulum has a length of 2 meters and a bob of mass 0.04 kilograms. It is held at an angle of theta, shown where cosine of theta equals 0.9. If the pendulum is released from rest, the maximum speed of the bob attained is most nearly which one of these? A, B, C, or D. Alright, so in this problem, let's talk a little bit about it before we start solving it. They do give us a mass of the bob. Now the mass of the bob is irrelevant as far as figuring out the velocity or as far as figuring out the period of the pendulum. So that's not required. Now, for the angle, the release angle, if they give you the release angle, do you use it to figure out the period? And the answer is no, you don't use the release angle to figure out the period. But in this problem, they're not looking for the period. They're looking for the velocity of the bob as it swings back to the equilibrium point. So we will use it because we will need the height. So this angle is required, and the strategy is this. The length of 2 meters, which is the length of the pendulum, is not the height. See, the bob starts here, it gets moved over here, and then released. The height is actually how far the bob is from here compared to there. So the difference between both of those two lines. So do not confuse the length of 2 meters as our height. No, this is it. So we're going to go ahead and use that angle to figure out what is that height. So between these two red lines, that's what we'll be looking at. First, let's go ahead and get our formula for the velocity. The velocity for this pendulum, we're going to go ahead and use the conservation of mechanical energy. And then we're going to go ahead and derive the formula. So we start with this. Mechanical energy initial is equal to mechanical energy final. So what's mechanical energy? It is the kinetic energy plus the potential energy. So let's go ahead and write those down. Kinetic initial plus potential initial is equal to kinetic final plus potential final. Next, of those four, there's two that we can get rid of. The instant we let go of the bob it's got no initial velocity. That instant the velocity will be 0, so therefore it's got no kinetic energy, so we're going to cancel that out. Once the bob's at the bottom of the swing at the equilibrium point, we're going to say that it's got no height. So our final potential energy is a 0 as well because it's got no height. So we only have these two values. Let's go ahead and substitute the values for it. For potential energy, it is mass times gravity times height. So I'm going to put mghi, height initial. Kinetic energy is 1/2 mass times velocity final square. And we're trying to solve for that velocity final. Alright, so keep that in mind. We need that velocity final. So we're going to go ahead and get rid of the half. I'm going to multiply both sides by 2. So it's going to go ahead and give me 2 mghi equals mvf squared. And then I want to get rid of the m's. So I'm going to divide both sides by m. So I end up with this. 2ghi is equal to vf squared. At this point, let me pause for a second and again point out that mass does not play a role as far as the movement of a pendulum. Alright, so the mass of the bob is irrelevant, and notice how it got cancelled out here. Alright, last step, I want to go ahead and square root the vf, so you can have it just vf, not vf square. So I end up with this 2ghi, and I square root the whole thing, equals vf. That's our velocity. Great. Now that we have that, we need to figure out what is the height. We still don't have that value. It was not given to us. Again, the length of the pendulum is not the height. They did not lift the pendulum all the way to 90 degrees. It was just lifted some amount theta. Alright, so we got to figure out the height. So that'll be our next part. Before I do so though, I'm going to rewrite this formula here and give myself a little bit more board space by erasing our derivation. Alright, so now let's talk a little bit about how we're going to get the height. The difference in height between this bob and the bob at this point. Alright, so this is what we're going to go ahead and do. We're going to go ahead and draw a right triangle right here, and this blue line that I'm drawing now going up and down, we're going to refer to it as y. That is from this point to that point, and what we're going to do is take the length and subtract it minus this blue y, and the difference is this gap between the red lines, which is the height. That is our goal. So first we need the length of this blue line. Alright, so let's go ahead and figure that one out. Notice how it's adjacent to the angle, so I'm going to say cosine of theta, it's equal to y over the hypotenuse, which is L. So then to get the hypotenuse, or to get the value of the y, I'll just multiply both sides by L. So it's really L times cosine theta, it's equal to the y, which is from here to there. Next, to solve for the height, again, the difference between both of these red lines is the total length minus the length of y. So it's going to be height is equal to total length minus the length of y. And I'm going to go ahead and substitute this value in. Height is equal to length minus y, which is length times cosine theta. That right there, that's our height. So now that we have the height, we're going to plug it into this formula to get our final formula we're going to go ahead and use to solve this problem. So it will end up looking like this. 2g, and then the height, we're going to substitute this L minus L times cosine theta. It's equal to velocity final. And this is all square rooted. Alright, so that is our formula to solve for the final velocity as the bob swings through the equilibrium point. Alright, so let's go ahead and plug in the values and get our answer. So it's going to be 2 multiplied times g, which we're going to just go with 10 meters per second squared. L is 2 meters minus 2 multiplied times cosine of theta. By the way, you know what the cosine theta is, right? Cosine theta is 0.9, so I'm just going to put 2 multiplied times 0.9, square root this whole value, and that gives us our velocity final. And let's go ahead and plug in values. So it's 2 times 0.9 gives us 1.18, and now we're going to go ahead and subtract. Sorry, 1.8, and we're going to go ahead and subtract 2 minus 1.8 gives us 0.2. So we have 2 times 10 meters per second squared multiplied times 0.2 meters, square root that, I'm going to multiply all of these, so that's going to give you 0.2 times 10 times 2 gives us 4. And our final answer, square root of 4, will be 2 meters per second squared. Oops. 2 meters per second. That's our velocity at the bottom of the swing for our bob. So the answer for problem number 34 will be letter C. Up next for us is problem number 35. It says, an object of mass m is attached to a horizontal spring stretched to a displacement a. So here we go. They grab it from here, pull it all the way to a. From the equilibrium, and is released undergoing a harmonic oscillation in a frictionless surface with period TO. So it's going to go back and forth, and the period is TO. The experiment is then repeated with a mass of 4m, 4 times as heavy. What is the new period? Alright, so the original period TO is 2 pi and then multiply times the square root of m over k. Now, since it's the same spring, the k stays the same, but this time we're going to quadruple the mass. So for a new mass, I'm going to put it number 1, it's going to be 2 pi square root of 4m over k. Alright, sweet. So now, what can we do here if the mass is 4 times bigger? That's why it's 4m. Well, we can go ahead and get the 4 out of the square root. Square root of 4 will give me a 2. So I'm going to go ahead and write this down. 2 pi and, hold on. So where did this 2 come from? It's the square root of 4 is 2. So I put it here in the front. And I also wanted to point out this. What is 2 pi multiplied times the square root of m over k? 2 pi multiplied times the square root of m over k is TO. So I'm going to substitute that here. So T1 equals double TO. So our answer to the problem is letter A. It will take, if you quadruple the mass, it's going to go ahead and the period will double. Our next problem is problem 36. In this problem, you're asked the following. A block of mass m is 0.6 kilograms attached to a spring with a force constant of 130 newtons per meters is free to move on a frictionless horizontal surface. The block is released from rest after the spring is stretched to a distance of a, which equals 0.13 meters. That instant, find the force on the block and its acceleration. So you get the block, pull it away, and the instant they let it go, what will be the acceleration of the block and how much force does the spring have as it's pulling in the block? Alright, so for this problem, here's the values that we have, whereas normally A is how much they stretched it. We refer to that as X, how much the springs is stretched or compressed. The formula we're going to go ahead and use for this one, there's 2 of them. The first one is the force. We want to know the force of the spring. It is K times X, the constant times how much it was stretched. So for the constant is given to us 130 newtons over meters, and it was stretched by 0.13 meters. So we go ahead and we'll multiply both of those, and that's going to give us the force for the spring. So 130 times 0.13 gives me 16.9. We're going to leave it at that, newtons. Now that we have that value, let's move on to the second one. They go ahead and they ask us to figure out the acceleration. How quickly is that block accelerating as it goes towards equilibrium? Alright, so force is equal to mass times acceleration here. And we're going to go ahead and isolate the acceleration by dividing by mass. So acceleration is really the force of the spring over the mass of the block. So the acceleration will be 16.9 newtons over the mass, which is 0.6 kilograms. So divided by 0.6, that's going to give us an acceleration of 28.2 meters per second square. That is the answer for part A and B, the force and acceleration for this block after it's been stretched. This also takes us to the last problem on this lesson for week 16. And this also brings us to the end of Unit 4 for AP Physics. Thank you so much for watching.